Hi everyone, today we're going to talk about electrons. If you watched my notes presentation on atoms in the periodic table, you should already know a little bit about electrons. But today we're going to get into the meat of why electrons are so important. So the first thing I want to mention is models of the atom. So we have Bohr's model, which said a bunch of things. It said the lowest energy state of an atom is called the ground state. Atoms can exist in various energy levels. So just like a person, they could be relaxed or a person could be excited. It's the same with an atom. An atom can be in a relaxed ground state or an excited high energy state. Bohr's model states that electrons move in exact orbitals around a nucleus, and I will explain more about what an orbital actually is. States that a quantum number n is going to be assigned to each, and the lower that number, the lower the energy of the atom. There's also the quantum mechanical model, which describes electrons as waves, which we'll talk about off and on throughout this class. And it also contains the Heisenberg uncertainty principle, which basically says it's impossible to know both the speed and the location of a particle at the same time. So you could either know how fast that particle is traveling, or you could know where it is, but you cannot know both at the same time. To define quantum numbers for you, they're basically numbers that help describe an electron's placement around an atom. The quantum number is going to indicate which energy level an electron could be found in, potentially. So the quantum numbers more or less kind of go along with these period numbers on the side, or the rows, as I should say as well, but they don't exactly match all of the time, and I'll show you why as we go forward. I made a copy of the periodic table and color-coded it for you with the different orbitals and energy levels and everything like that. But before we get there, I'd like to talk about electron dot structures, because you are absolutely going to be required to draw electron dot structures for me, and you're going to have to know about valence electrons, because valence electrons affect pretty much everything else that we do in this class. So a valence electron is an outer electron. The valence shell is the outermost electron shell around an atom. So atoms can have, potentially, depending on which atom it is, hundreds of electrons. But when atoms are participating in chemical bonds, the only electrons that truly matter for that are the outermost electrons, most of the time. There are exceptions to that, but most of the time. So the valence shell, or the outermost shell, is the one we care about. In an electron dot structure, each dot is going to represent one of those electrons, and there's a maximum of 8 valence electrons in that shell. If an atom is found in group 1 on the periodic table, when that atom ionizes or gains a charge, something's going to happen with its singular valence electron. So group 1 always has 1 valence electron. Group 2 is going to have 2. Group 13 has 3, group 14 has 4, 15 has 5, etc., all the way up to 18, which has 8 valence electrons. Now that's in bold because 8 valence electrons is a full outer shell. And if you remember from my periodic table notes presentation, group 18 is unreactive because it has a full valence shell of 8 electrons. I would like to note that the reason that it jumps from group 2 to group 13 right up here is because all the groups in the middle of that are referred to as the transition elements. And when those ionize, things happen with differing numbers of electrons in their outermost shell. So they can actually have different numbers of valence electrons depending on what's going on with them. So that's why it skips from group 2 to group 13. That is not a typo. Okay, so here's some practice ones that I'm going to show you with how to draw electron dot structures. Now, If you want to go along with me and get the most out of this, you're probably going to want to have your periodic table next to you or pulled up or Google it on your phone or something, because it makes more sense when you're looking at the periodic table directly. Magnesium, for example, or Mg as its abbreviation is in group 2, which means it has 2 valence electrons. So magnesium should have 2 dots around it somehow, some way. So if you're just going to draw the electron dot structure, you write the chemical symbol and you draw 2 dots around it. Okay? No, the 2 dots may not be close to one another. So you may not draw magnesium like this. The reason for that is because electrons tend to be as far apart from each other as possible before they pair up. So when you have atoms that have more than 4 valence electrons, you have to draw all 4 before you can start pairing them up. So this is wrong, this is right. However, you could also go like this. That's fine because electrons do move around. So it doesn't necessarily have to be one on the top, one on the bottom. It could be one on either side, but they may not be in a pair. Okay? So next, let's go to lithium. Lithium is found in group 1, so it has 1 valence electron. So when we draw that electron dot structure, we just have 1 electron around it. And again, that could be on whatever side you want it to be on, because there's not even a chance for a pair. Argon, on the other hand, is found in group 18, so that's going to have 8 valence electrons. Now, when you draw argon, you're going to end up with 4 pairs because there's 1, 2, 3, 4, and then 5, 6, 7, 8. Now, it's going to seem a little bit ridiculous to you how I'm about to draw this, but trust me, it matters, and I will show you why. But you're going to have to draw it like this. You're going to go 1, 2, 3, 4, 5, 6, 7, 8. And you could be asking yourself, well, why couldn't I just go pair, 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 pair? And you could have for this one, but that's not how electrons fill up their areas. That's not how that works. And it matters when you have odd numbers of electrons. So let's say, for instance, over here, let's say I was going to do nitrogen. Nitrogen is found in group 15 and has 5 valence electrons. So if you started doing it pair for pair until you ran out and you did 1, 2, 3, 4, 5, that's wrong. Because nitrogen does not have 2 pairs of electrons. It has 1 pair of electron and 3 unbonded electrons or unpaired ones. So the correct way to draw nitrogen is actually 1, 2, 3, 4, 5, because that has 3 unpaired electrons. And as you will learn later, and I will explain later, that leaves 3 open spaces for bonding, which nitrogen does have. In this case over here, paired electrons cannot bond, therefore this is incorrect. So it does matter how you draw these electron dot structures. So as a rule of thumb, if atom X has 5, 6, whatever electrons, again, you have to unpair all of them before you can start pairing them up. So you always have to go 1, 2, 3, 4, 5, 6, 7, 8, or until you run out of electrons. So just remember that going forward. The next thing I want to talk about is electron configuration. So electron configuration, rather than just dealing with the valence shell, deals with the total number of electrons in any particular atom. Those electrons are going to try and obtain the lowest energy possible. So that goes back to when I was talking about ground state. They like to be in a resting state, a low energy state, because maintaining a high energy state or configuration is not sustainable. Like imagine that you had to spend 100% of your time sprinting around the track. That's not going to work. That's not sustainable. So atoms, they like to be in a relaxed state as much as possible, otherwise known as their ground state configuration. So there's a couple of rules for how ground state electron configurations are put together. There's something called the Aufbau principle that states that each electron is going to occupy the lowest energy orbital possible, which again is basically a reiteration of what I already said. They like to be the lowest energy possible. This diagram here, I don't tend to use it a lot because while it makes sense, it's easier for me to visualize configurations a different way. But if you like this diagram, you're more than welcome to use it because it tells you if you start at the upper left, you should go 1s, 2s, 2p, 3s, 3p, 4s, etc., etc. And that's how you're reading that diagram following the arrows. So if that helps you, feel free to use it. I won't refer to it a whole lot, but I'm handing it to you in case you want it. The Pauli exclusion principle talks about electron spins. So electrons do spin as they orbit a nucleus. So within the same atomic orbital, you can have 2 electrons. Each orbital can have 2 electrons, but they have to have opposite spins, which will make sense more when we start drawing out orbital diagrams. And then there's Hund's rule, which says single electrons with the same spin must occupy each equal energy orbital before additional electrons with opposite spins can occupy the same orbital. So that is a mouthful, but basically what that means is that when you are drawing out an orbital diagram, you have to put all the up arrow or upward spin electrons in one at a time before you can go back and start filling in the downward spins one. Again, I will get there and you will see what I mean by that. One thing that you do have to be aware of though is that each energy level, the S energy level, the P energy level, the D and the F, have a certain number of orbitals. So the S energy level is going to have 1 orbital and therefore can contain 2 total electrons. The P energy level has 3 orbitals and therefore can contain 6 total electrons. The D energy level has 5 orbitals and therefore can contain 10 total electrons, and the F energy level has 7 orbitals and therefore can contain 14 electrons. Because remember, each orbital can have 2 electrons. Okay? So to give you a visual idea when I'm talking about orbitals, this kind of shows you visually how orbitals are going to look around an atom. So one atom can have a bunch of these orbitals together around it. So one atom could have several s orbitals, several p orbitals, several d, several f surrounding it at one time, but each of those orbitals has a slightly different shape and orientation, especially depending on how many of them exist and what other orbitals are present. So an s orbital is going to be spherical. The p orbital kind of looks a little bit more smushed. The d orbital is even more smushed than the p, but can have this weird donut looking shape sometimes. And the f orbitals can get crazy. They look like little tiny water balloons, and then there can be some like stacked donuts. They're weird. We're not going to focus too much on the shapes though, nor will you have to draw any particular shapes of these orbitals around atoms. But when you're looking at this, imagine that the center, the nucleus of the atom, was the origin spot in this graph. Okay, so this is the color-coded periodic table that I was telling you about. So when we're looking at the periodic table, and if you recall I said this in class, it's basically the biggest cheat sheet that you'll ever get, ever. So all the s orbital represented electrons, so those are going to be this purple color. The d orbital is going to be this green. The p orbital's this orange over here, and the f orbital is going to be represented in blue down here. Please note though that helium is still technically, that spot falls within the s orbital. So one thing you have to understand when we're talking about electrons is that each space on the periodic table not only represents an atom, but if you're counting orbitals and you're counting electron configurations, it also represents 1 electron. So what I mean by that is that if we wanted to do the electron configuration for hydrogen, well, hydrogen has 1 electron, and therefore its configuration would be accordingly, or would act in accordance with that. Helium has 2 electrons, so if you were to count all the way over to helium, you'd go 1, 2 electrons. Lithium has 3, so you'd go 1, 2, 3 electrons. Beryllium has 4, etc., etc. You see how I'm reading it from left to right. Okay? So, like I said during the atomic presentation, your atomic number here, your number of protons, also represents your number of electrons in neutral state. So remember that. This is another picture of the periodic table, still color-coded. The color coding is a little different, but it does tell you, it actually tells you which orbital you're dealing with in which area and what quantum number is assigned to that particular energy level. So period 1, this first top row right here, only contains the S energy level, the 1s specific orbital, okay? But the row 2 here has the 2s, but also the 2p. Row 3 has 3s and 3p. Row 4, though, has 4s, 3d, and 4p. So you have to pay attention to what number is assigned for which particular thing. So I highly recommend that you take this picture of the periodic table, copy it for your own records so that you have that, because it's going to be super important when you're drawing electron configurations. Okay? So I'm just going to kind of break right into writing out these full electron configurations, because it's just going to be confusing until you see me do it. So if I wanted to write the electron configuration for hydrogen, hydrogen is going to have 1 electron, okay? So to represent what quantum number, what orbital, and what electron number it is, we write down all of that information. So you see hydrogen here, and hydrogen is in that 1s orbital space. So you're going to write 1 and s first and foremost. And it has 1 electron, so we put a little 1 exponent there, and that's it, because it's the first one. Okay, so that's pretty easy. If I wanted to do helium, that has 2 electrons, so 2 electrons. And if I wanted to write the configuration, well, it's still within the 1s, as you see here. So we're still going to write 1s, but now we have 2 electrons, so we're going to write 2. Each time you get to a new orbital, or even a new energy level, you have to write another number. So lithium, down here, still has electrons that are in the 1s orbital. So we would write 1s2 to kind of summarize those 2 electrons, okay? Because again, we're reading the periodic table from left to right. And then now lithium is here in the 2s orbital. So we have 2s, and it occupies 1 space there, or 1 electron there. So we have a 1. Now, if that's confusing to you, look at what our exponents add up to. 1 plus 2 equals 3. Lithium has 3 electrons. So that's the function of those numbers right there. Helium has 2 electrons, therefore you're 2. Hydrogen has 1 electron, therefore that little exponent 1. Okay? So talking about carbon, which is over here, we've gotten slightly more complicated. Carbon, if you count over 1, 2, 3, 4, 5, 6, there's 6 electrons, all in those respective energy levels and with those respective orbitals. So you have to include that 1s2 to summarize your first row. You have to include 2s2 because there's 2 total electrons in the 2s orbital. And then once you get to 2p, because carbon is within the 2p orbital, you count over how many spaces within that orbital. So it has 1 space in it, 2 spaces. So you have 2 here. And to just check our work, carbon has 6 electrons to 4, 6, we have the proper amount of electrons there. Okay? Silver, on the other hand, is a little bit more complicated down here. Silver is going to have a lot of stuff to do with electron configuration, okay? So starting from the beginning, you have to count all of these individual squares all the way down till you get to silver. So for the 1s orbital, we have our 1s2. For the 2s, we have our 2s2. For the 2p, we are going to have 2p6 because there's 6 total spaces here. Then we go down a row. 3s2. We go over 3p6. We go down a row, 4s2. Moving over, you see that this is no longer 4, it's 3d. So we write 3d10 because there's 10 total spaces here, and if you count them, you can check my work, there are 10. Moving over, we go back to 4p, and again, 6 spaces in a p orbital. Then we move down a row again, and we get 5s2, and then we've found the particular orbital that silver is in. So it's in the 4d, and we count over 1, 2, 3, 4, 5, 6, 7, 8, 9. So our last one is 4d9, okay? And if we were to add up all these exponents together, we would find that there's a total of 47 electrons there. So you see how this kind of gets longer and a little bit more complicated as we keep going. All right? Because full electron configurations are kind of a pain at times, for the longer ones, i.e. this one, you can write it a little differently. You can write it using a summary, essentially, of the nearest previous noble gas. So if you remember, noble gases are all down here. All right. Some of these electron configurations change based on where their noble gas is. Some of them don't really. So I'll show you what I mean by that. Hydrogen does not have a previous noble gas. There's nothing before hydrogen. So hydrogen's electron configuration would remain the same as 1s1. Carbons, here, you could write it either way. You could write it in a noble gas configuration, or you could write it normally. It doesn't really matter because its configuration is not complicated. But to show you what it would look like, if you went backwards on the periodic table, helium is the next previous noble gas. So instead, you could put helium in brackets, and you could just move on. So starting at helium, moving down, you have the 2s2 and the 2p2. Which, I mean, comparing that to our previous carbon electron configuration, because the full one was 1s2, 2s2, 2p2, that's not really that different. Like, it's pointless to use noble gas configurations to write carbon. But when you get to the longer ones, like, say, silver, for example, it becomes a lot easier, okay? So once again, silver's right here, and you go backwards until you hit a noble gas. In this case, krypton is the one that we're going to be using. So you would put krypton in brackets, and then you just count until you hit silver. So moving down, you have 5s2, and then 4d9. And then you're done. See how we've summarized it with krypton? We're saying, hey, silver matches krypton's electron configuration, but also has it also has 5s2 electrons and 4d9 electrons, okay? So noble gas configurations are faster, especially for atoms that are farther down the periodic table. But for these ones up here, it's pointless to use that. Okay? The last thing I want to talk to you about is writing orbital diagrams. Orbital diagrams are, for instance, basically just taking this big giant electron configuration and essentially summarizing it a little bit more. So when I was talking about that rule that talked about opposite spins, up arrows and down arrows, this is what we're going to use that for. So in your notes, I provided for you the electron configurations of each of these because you need that configuration to write out the orbital diagram. All right. So if you recall, each orbital can hold 2 electrons, okay? Each orbital can hold 2 electrons. We're going to represent orbitals with boxes. So in S energy levels, 1, 2, 3, 4, whatever, there's only going to be 1 box because there's only a total of 2 electrons in the 2s and the 3s and the 4s and so forth. So each one of these is only going to be represented by 1 box. So S equals 1 box. P energy levels, P2, P3, P4, P5, P6, they can hold 6 total. Each orbital can hold 2 electrons, so P needs 3 boxes. D can hold 10 total electrons, so D is going to need 5 boxes. And if we were to get all the way to F, F has a total of 14 electrons, so F is going to need 7 boxes. Once again, just watch my examples, it will become a little bit more clear. So to just kind of reiterate, hydrogen's electron configuration is 1s1. Okay? So S needs 1 box. We already said that. So to do that orbital diagram, you would draw 1 box. There is 1 electron in that box, so you put 1 arrow. Okay? That's it. If I wanted to do helium, on the other hand, its configuration is 1s2. But again, I would need 1 box, okay? But this time, there's 2 electrons with opposite spins, okay? For lithium, its electron configuration is 1s2, 2s1. So if we wanted to do that, the 1s is going to get a box, and the 2s is going to get a box. And you go and you fill up the 1s, you go 1, 2. The 2s only has 1, so you're going to go 3. Okay? That's kind of how that's going to work going forward. Now I need to erase this to have room to do carbon, so I will. Okay, let's talk about carbon. Carbon's electron configuration I'm going to write over here. Carbon has an electron configuration of 1s2, 2s2, 2p2. Okay? So I'm just going to expand it a little bit. That 1s2 is going to get 1 box. The 2s2 is going to get 1 box because, again, s's have 1 box. The 2p is going to get 3 boxes. Okay? The 1s2 has 2 electrons, 1 up, 1 down. 2s2 has 2 electrons, 1 up, 1 down. The 2p, on the other hand, this is where that exclusion principle comes into play. You may not start pairing up electrons until all these boxes have at least 1 in them. So 1, 2. Okay? If it had had more electrons, if it had, say, 4, you could have gone 1, 2, 3, and then paired 1 up. All right? So, silver. And I'm going to have to erase quite a bit of this to have enough room. Silver is pretty extensive. Okay? So you're going to go ahead and we're going to stack these once again. Look at the electron configuration for silver. It is in your notes. It has a 1s. It has a 2s. It has a 2p. It has a 3s. It has a 3p. It has a 4s. It has a 3d. It has a 4p. It has a 5p. S, and it has a 4D. So that's pretty big. We're getting pretty sizable here, okay? 1s2, 2 electrons. 2s2, 2 electrons. 2p, remember we get 3 boxes. There's 6 total electrons. We have to fill them in before we start pairing. 3s is 1 box, 2 electrons. 3p is 3 boxes, and it's also full, so 1, 2, 3, 4, 5, 6. 4s is going to be 1 box, 2 electrons. The 3d is also full, but this one is going to need 5 boxes. It is full, so again we fill it up. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5 for a total of 10. 4p, 3 boxes. It is full. 1, 2, 3, 4, 5, 6. 5s is 1 box. It is full. The 4d is not full. So here we have 5 boxes again. Oops, let me move thing. Okay. Remember, this last one was 4d9, and you can see that in your notes. So as we fill it up, we go 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay? This last box only has 1 electron. That is the complete orbital diagram for silver. They are long, you guys, they are long. But as long as you know the electron configuration for your atom, they are not impossible. All right? So that is everything I have to talk to you about today, right now. Please see me if you have questions, because I know that this can be confusing. But other than that, have a good day.